Math of Mr. Williams, example 1, writing a linear function using a graph. Use the graph to write a linear function that relates y to x. So let's go ahead and write down our linear function. We have y equals mx plus b for our format. We know all we have to do is find the slope, which is the m, bring down our variable x, and then it's plus or minus whatever the b is. So in other words, if it's positive, we put plus, and if it's negative, we're going to put a minus. So let's go ahead and find those items. So we can see the first off, the y-intercept, our starting location, would be right here at a -3. So we know now it's y equals a -3 at the end. Now to find the slope, remember slope is rise over run, or we can use y2 minus y1 over x2 minus x1. All right, so in this case, we can quickly use just rise over run. We can count boxes. So if we start at our y-intercept, we can count up 1, 2, 3. So this would be a rise of 3. And then we would go across 1, 2 for our run of 2. So we have 3 over 2 for our slope. So we're going to come back and put 3 over 2 where the box was, bring down our variable x, and now we are done. We've completed our linear function. Math of Mr. Williams, example 2, writing a linear function using a table. Use the table to write a linear function that relates y to x. So here we're looking at the table. We know the y value is going to represent our rise. So if we're looking at the rise, we see it is decreasing each time by 2. All right. And now if we go over to our x, which is our run, because it goes from left to right, we have a -3 to -2. We see that is actually an increase of 1 again, and then from -1 to 0, that is an increase of 1. You're heading in the positive direction. All right, so our rise over run would be a -2 over 1, or just a -2 for our slope. All right, now to find the y-intercept, remember to find the y-intercept, we're looking for where x equals 0, and lo and behold, we did find that. It is right here. Our y-intercept will be whatever the y value is. So in this case, we have b in our y equals mx plus b being a +3. All right, so if we substitute all our numbers in, we have y equals, our slope is -2, x plus 3. Now let's go ahead and graph it. All right, so our first order pair will be a -3, 9. So we go left to -3 and then up to 9. Our next one would be -2, 7. Then we have -1, 5. So we start at the origin, move left 1, and then up 5. Then we have 0, 3, our y-intercept. So we don't go left or right because it's 0 for our run, but we do go up 3 spaces. All right, let's connect our dots. And there's our linear function. You can quickly see there's our y-intercept at that 0, 3. And we can see if we did our rise over run based on our graph alone, 1, 2 spaces, and over 1, this would be a -2, and then 1. So it'd be rise and run again. Just to check it, we would see a -2 over 1, or just a -2. So now we've written our linear function and checked it. Math of Mr. Williams, example 3, identifying linear functions using graphs. Does the graph represent a linear or nonlinear function? Explain. So on the first one, we see this is a U shape, this is quadratic. This is not a linear function. It is not a straight line. On the second one, we see it is a straight line. So that makes it a linear function. Math of Mr. Williams. Example 4, identifying linear functions using tables. Does the table represent a linear or nonlinear function? And explain. So if we look at the first one, we see our rise and run. So remember, our y value is our rise, and the x value is our run. So we're looking at our rise. It looks like it's decreasing by 6 each time. And our run looks like it is increasing by 3 each time. So our rise over run would be a -6 over 3, or just a -2 for a slope. All right, the key here is constant change. There has to be constant change on the top and the bottom, or with our rise and run. in order for it to be a linear function. Notice the top is increasing by 3 each time, and the bottom is decreasing by 6 each time. All right, let's go into B and see if it holds true. We have our rise, and we have our run. All right, on top, we can see it is increasing by 2.5, then it increases again by 2.5, and then again by 2.5. That is constant. All right, we see from 2 to 9, it is increasing by 7, but then from 9 to 20, it's increasing by 11, and from 20 to 35, it is increasing by 15. That is not constant. That is not the same increase. There is no rise over run in this case because the numbers continue to change. So this one is nonlinear, and the first one was linear. The key is to look for that constant change for the rise and the run. Math with Mr. Williams, Example 5. Identifying linear functions using equations. Which of the following equations represents linear functions? Explain. So we're going to jump over to Desmos, and we're going to type each one in and see what they look like. Okay, let's go ahead and start off by graphing our first equation on Desmos. Our first one being y equals 3.8. And you can see that is a linear function. Let's go to the second one. We had y equals, we have a square root of x, so we have to come down here to our keyboard, pop it up, hit the square root sign, and then we're going to put an x in. You can see that is not a linear function. And the third one, we had y equals 3, hit shift and the arrow up, allowing us to put the x for our exponent. And you can see that is definitely not a linear function. It curves upwards, making it an exponential function. On to 4, we have y equals 2 divided by x. You can see that is definitely not a linear function. On to 5, we have y equals 6 times the parentheses of x minus 1 in parentheses. You can see that is a linear function. And our last one being x squared minus y equals 0. And you can see that one is not going to be a linear function. It's an actual quadratic. So now we've identified all the ones that are linear functions, which in this case, we had the first one, y equals 3.8, and y equals 6 times parentheses x minus 1 and parentheses as linear functions.